Have you ever looked out the window on maybe a rainy day and just wondered, where does all that water come from? Or, when it snows, or even hails. It's kind of like the sky's putting on a show, isn't it?
Hmm.
Today, we're going to take a really cool deep dive into the story of how water falls from the sky. What we call precipitation. Think of it like a grand adventure for every single drop of water. Our mission today, as we dive into the research we've gathered, articles, scientific papers, that sort of thing, is to understand exactly what precipitation is. How it forms, why it's different in different places, and even how we measure it. We want to explain it all in a way that's super clear, maybe even a bit fun, like we're just figuring it out together for the first time.
And what's really fascinating here, I think, is that this isn't just about puddles or, making snow angels. Precipitation is basically Earth's main way of getting fresh water from the atmosphere down to the ground. It's super important for, well, everything. From the tiny plants maybe growing in your garden to the huge rivers flowing out to the ocean, understanding it really helps us understand our whole planet. It's fundamental.
Okay, let's unpack this then. What exactly is precipitation? If you had to give it I don't know, a simple definition.
Right. Precipitation is really just any form of water, liquid, or solid that falls from clouds from the atmosphere back down to the Earth. So it could be liquid, like rain or drizzle, or it could be solid, like snow or sleet, or even those hailstones. You could maybe think of the sky or the clouds as a giant water fountain, maybe.
Mhm.
And precipitation is just how the water comes back down.
Okay, so we've got the everyday rain, obviously, then the fluffy snow, perfect for, well, snowmen, and then those sometimes bumpy, even damaging hailstones. So, what does this all mean for us practically? Why should we care if it's rain or snow falling?
Well, connecting this to the bigger picture, these different forms are actually crucial. They're not interchangeable. Rain, snow,
Ah,
they water our plants. They fill up our lakes and rivers. And the type of precipitation even helps decide what kind of plants and animals can actually live in different places. It's
yeah,
like the Earth's own natural watering system, but with different settings, you could say.
right, that makes sense. But here's where it gets really interesting for me. How does the water get up there into the sky to fall down in the first place? Is it like a big sky faucet just turning on? Our sources talk about powerful atmospheric forces. That sounds pretty dramatic, almost like something out of a sci-fi movie.
Huh. Well, it is pretty powerful, but maybe think of it less like a faucet and more like, a giant invisible elevator system in the atmosphere. This elevator carries water, but in a gas form, water vapor. It picks it up from oceans, lakes, even plants. Now, when that elevator goes up really high in the atmosphere, it gets very cold. And just like your breath on a cold day, that invisible water vapor turns into tiny little water droplets or ice crystals that kind of hold hands, forming clouds. Eventually, those droplets or crystals inside the cloud bump into each other. They grow bigger and heavier. And once they get too heavy for the air currents, the elevator to hold them up, whoosh, down they come as precipitation. But, and this is key, there are different ways this elevator gets pushed upwards in the first place. Different lifting mechanisms.
Okay, so these powerful forces are the things pushing the elevator up. Our sources list some fantastic names for these sky machines that make precipitation happen. Mid-latitude cyclones, orographic lift, convective activity, and tropical cyclones. Let's start with mid-latitude cyclones. That sounds like some kind of, I don't know, big swirly atmospheric dance.
That's actually a pretty good analogy. Think of them as huge, slow-motion weather systems, like enormous swirling dancers in the sky. They happen in the mid-latitudes, where most of us live. They form when warm, moist air from the tropics meets cold, dry air from the poles. They don't mix easily, so they start to swirl around a center of low pressure. Within these systems, you have fronts. A warm front is like the warm air gently gliding up and over the colder air. This slow, gentle lift tends to make steady, widespread rain or snow, often lasting for hours. A cold front is more like a bulldozer. The cold air aggressively pushes under the warm air, forcing it upwards really fast. That rapid lift often creates more intense, shorter bursts of rain, think heavy showers, sometimes even thunderstorms. These cyclones are major rainmakers for large areas.
Okay, that covers those big regional storms. What about orographic lift? That sounds a bit technical, but I bet the idea is pretty cool.
Oh, this one is definitely cool, and it's all about geography. Orographic just means related to mountains. So imagine the wind carrying lots of moist air, maybe blowing in from the ocean. It's cruising along, and then bonk, it hits a giant mountain range. The air can't go through the mountain, so the only way to go is up. It's forced up the slope. And just like our elevator going up, as the air climbs the mountain, it gets colder. The higher it goes, the colder it gets. This cooling makes the water vapor condense into clouds, and then it drops all its water, rain, or snow right there on that side of the mountain, the side facing the wind. We call that the windward side.
Ah, so the mountain acts like a ramp, forcing the air up and squeezing the water out.
Exactly. But then what happens when the air goes over the top and starts coming down the other side, the leeward side? Well, as it goes down, it warms up again. And now it's lost most of its moisture, so the air becomes really dry. This creates something called a rain shadow on the leeward side. It can be incredibly dry there, sometimes even forming deserts, right next to a really wet mountainside. It's like the mountain took all the water for itself.
Wow. And our sources actually mention a real-world example of this, the Reynolds Creek watershed out in Idaho. It shows, quantitatively how much more rain falls on that windward, mountain-facing side compared to the other side.
Yes, it's a classic example. Orographic lift is hugely important for determining regional climates all over the world where you have mountain ranges.
Okay, next machine, convective activity. Is this when the sky gets kind of bubbly, like on a hot day?
Bubbly is a good word for it. That's exactly the idea. Think of a really hot summer afternoon. The sun beats down and the ground gets super warm, like a giant frying pan heating up. This heats the air right above the ground. And hot air, as you know, likes to rise. It's less dense, more buoyant. It wants to go up, just like a hot air balloon. If there's enough moisture in that rising parcel of hot air, it shoots upwards really fast and high. This rapid upward movement builds those tall, towering clouds, cumulonimbus clouds, the ones that look like giant cauliflower heads or anvils. These are the clouds that give us those quick, heavy summer thunderstorms, sometimes with hail and gusty winds. And it's often very localized. It might be pouring rain on your street, but your friend across town might not get a single drop. That's convection.
Right, those sudden downpours. Okay, and finally, the really big one. Tropical cyclones, what we often call hurricanes or typhoons. These sound like supersized rain machines.
They absolutely are. Tropical cyclones are like giant spinning engines powered by warm ocean water. They only form over really warm tropical seas, usually above 26.5 degrees Celsius or about 80 Fahrenheit. They suck up enormous amounts of heat and moisture from the ocean surface. This fuels the storm. The air spirals inwards towards the center, rises rapidly, cools, condenses, and releases just a huge amount of rain. But the rain isn't just one big blob. It usually falls in distinct spiral bands, kind of like the stripes on a candy cane, rotating around the storm center. And the very heaviest rain, the most intense part, is typically found in the eye wall. That's the ring of powerful thunderstorms immediately surrounding the calm eye at the very center of the hurricane. They can dump incredible amounts of water.
Okay, so we have these different amazing sky machines. The swirling cyclones, the mountain ramps, the hot air balloons of convection, the giant ocean-powered hurricanes. But that leads to the next question. Why doesn't it rain or snow the same everywhere, all the time? Why do some places get loads of precipitation and others, like deserts, barely any? And why has it changed so much with the seasons? It's definitely not spread out evenly, is it?
Not at all. That unevenness raises a really important question. Why isn't the whole world equally wet? And the answer lies in a combination of factors working together on a global scale. You've got these huge planet-wide air circulation patterns, sort of like massive conveyor belts in the atmosphere that generally move moisture around. Then there's how close a place is to the ocean. Oceans are the main source of water vapor, so coastal areas often get more rain than places deep inside large continents, which can be much drier. And of course, those mountains we talked about, orographic lift, they create very distinct wet and dry zones. It's a complex geographic puzzle.
And the seasons play a huge role too, right? Our sources specifically mention how precipitation varies dramatically with the seasons. Like the Pacific coast of the U.S., which tends to have really wet winters but quite dry summers, that's totally different from the Midwest, which often sees a big peak in rain during the summer months, thanks to that convection we discussed. It's like different regions have completely different rain schedules built into the year.
It's exactly right. These schedules are driven by the tilt of the Earth and how solar energy shifts throughout the year. This changes the position of major weather features, like the jet stream or belts of high and low pressure. For example, the rainy season in many tropical areas is linked to the movement of a band of rising air near the equator called the ITCZ, the Intertropical Convergence Zone. Its position shifts north and south with the seasons. And it's not just the regular yearly seasons. There are also bigger, longer-term climate patterns that shake things up. Things like El Nino and La Nina. These are major shifts in Pacific Ocean temperatures that can totally change weather patterns across the globe for months or even years. They can cause droughts in some places and floods in others, places far away from the Pacific even. So yeah, the sky has a pretty complicated calendar for delivering its water.
Okay, so we have average patterns, seasonal shifts, big climate cycles, but sometimes the sky just goes completely wild, doesn't it? It doesn't just drizzle, it pours. or dumps an absolutely crazy amount of snow. Our sources mention extreme events and even world records for precipitation. Can you even imagine getting like a ton of rain all at once?
It's hard to fathom sometimes, but yes, these extreme events happen. While the averages tell us the typical story, it's often these outliers, these extreme rainfalls or snowfalls, that have the biggest impact on us. They can cause devastating floods, trigger landslides, or bury cities under snow. There are official records for the most rain or snow ever recorded in, say, an hour or 24 hours or even a year. These records really show just how powerful these atmospheric processes can become when all the conditions align perfectly. Nature can be incredibly intense.
So, how do we even know how much rain or snow falls? I mean, is it really just putting a bucket outside?
All right.
Sources talk about measurement and rain gauges, and apparently this goes way back to ancient times.
Huh. Well, the basic idea isn't too far off from a bucket, but it's a bit more scientific now. And yes, people have been trying to measure rain for a very, very long time. Our sources mention evidence of rain gauges being used way back in ancient India, maybe as early as the 4th century BC. Likely for agriculture, trying to figure out water availability for crops. Today, we have really advanced tools like weather radar and satellites that give us a great picture over large areas. They can estimate where rain is falling and how heavily. But for the most accurate measurement right at a specific spot on the ground, the best way is often still a good old-fashioned collecting gauge. Basically, a precisely designed container like a cylinder with funnel that collects the rain. It might have a ruler inside, or nowadays often an electronic mechanism like a tipping bucket that measures the amount automatically and sends the data off.
And I saw mention of even more specialized gauges, like something called the Knifer shielded gauge. It's designed to reduce wind effects, especially when measuring snow. Why all the fuss about getting the measurement just right? Why is it so important to measure it carefully?
The shield is really important, especially for snow. Wind can blow snow over the opening of a simple gauge or even blow snow out of it, leading to measurements that are way too low. The shield helps create calmer air around the gauge opening for a more accurate catch. And why the fuss? Precision is absolutely super important here. We connect this back to the bigger picture. Knowing exactly how much rain or snow falls is critical for so many things. It helps water managers plan our water supply, how much is in reservoirs, how much might be available for drinking water or farming. It's absolutely essential for predicting floods and warning people, or for monitoring droughts. This has huge impacts on safety and the economy. And for scientists studying climate, having accurate, consistent, long-term records of precipitation is indispensable. It lets us see how patterns are changing over decades, understand the effects of climate change, and check if our climate models are getting things right. There's even an international body, the World Meteorological Organization, the WMO, that sets standards for how these measurements should be taken everywhere, so we can compare data from different countries reliably. They even work on formulas to estimate the theoretical maximum amount of precipitation that could possibly fall in a given place. PMP, probable maximum precipitation, which helps engineers design dams and bridges to withstand even the most extreme future possibilities.
Wow. Okay, what a deep dive that was. We've really journeyed from just understanding what precipitation is,
Yeah.
that amazing water falling from the sky in different forms, all the way to exploring those incredibly powerful sky machines that create it, like those huge swirling mid-latitude cyclones, the mountain ramps causing orographic lift, the bubbly convective activity, and those massive tropical cyclones.
Indeed. And we've seen why water doesn't fall evenly everywhere, right?
Yeah.
How it changes dramatically with location, with the seasons, and even with larger ocean patterns like El Nino. And how people, for literally centuries, going back to ancient India, have figured out ways to measure these incredible events, refining tools right up to modern shielded gauges and satellite estimates.
So what does this all mean for you listening right now?
Well, hopefully, the next time you see rain pouring down, or watch snowflakes drifting, or maybe even hear hail clattering, you'll know it's not just random weather happening. It's part of this grand, intricate global system. It's powered by these incredible atmospheric forces we talked about, all part of what makes our planet the vibrant, watery, living place it is. You're seeing real science in action.
Which I think raises an interesting final thought or question. Now that you know a bit more about the amazing journey of water from the sky, what surprising new things might you notice or wonder about regarding the rain or snow that falls right there in your own backyard? What local weather patterns might spark your curiosity now?
Exactly. Keep observing, keep asking questions, and definitely keep exploring the incredible world around you. Thanks so much for joining us on this deep dive.